Good afternoon, professors. I am Zikin, and today I'll be presenting to you Streamsight, my FYP project that I've been working on. This will be the flow of the presentation, starting off with background to provide some contextual information, the gaps that have been identified, the design and the results of Streamsight, followed by some future work that can be considered, and the concluding remarks. To start off with background, I would like to start with the question on why recommender systems. And it has been shown that recommender systems have an economic benefit for companies that engage these systems, boosting revenue up to over 30% through better sales and user engagement. Well, our next question would then be why recommender system, or RS for short. And we can simply define the RS as a information filtering system that takes in data and run it through some algorithm, and it then outputs the user likely preference or decision on the various platforms that it is applied to. And several recommender systems have been developed over the many years. And here in our project, we are more interested in building a toolkit for RS. And a toolkit can be simply defined as a collection of tools, libraries, and frameworks that helps developers train, build, and eventually deploy the recommender system into its offline or online setting. And in fact, a toolkit tends to follow this pipeline structure: the load and pre-processing, the data split, training and evaluation of the RS, followed by further tuning if need be. And here are some toolkits and libraries that are very popular on Python. And we can see some familiar names like Ragbow. And in fact, numerous toolkits have been developed over the years to unify the various standards and to provide a framework to evaluate some of the complex RegSys algorithms like the ones listed here. The scope of the project will not consider the various algorithms as we are focused on building that framework in the toolkit. And now it leads us to the question on what is the problem then? Well, in this study, the researcher actually did a ranking of 20 algorithms across different data sets and matrices. And what was found was that the item KNN, a baseline model, performed the best on average. And this is a really counterintuitive finding, which differs from the results of many different published papers, which was highlighted earlier. And we then now ask ourselves, whose evaluation is correct? The new complex algorithms that have been published, or this paper that highlighted that the baseline model performed better than these papers, leading to the gaps that we have identified. And in Prof. Soon's paper, he highlights that in fact, what we should consider is not the matrices itself, but rather how the matrices are calculated when we evaluate some of these RS. And he also then points us to two other issues that stem from a neglection of the global timeline, that is data leakage and an oversimplification of the user preference model. He goes on in his next paper to further expound on this topic, where he highlights that the user decision making is not a static item user interaction, but rather a dynamic changing one, which is a complex form of decision making. And this current assumption is now not yet made in the offline setting. And with Prof. Soon's paper, what we did was we studied the 12 existing toolkits, all of which are published on top impact journals like the ACM-IR. And we can categorize the gaps into three umbrella terms listed here. The first, the data leakage from the split scheme. Second, an ambiguous metrics being defined during evaluation. And third, an inadequacy in the online simulation. And to bring back the gaps to the pipeline defined earlier, the first issue pertains to the split phase, the second in the evaluation phase, and the third in the train and evaluate phase. And before I continue on, I would like to provide some definition of the terminologies here so that we are grounded in the definition. The data leakage is defined when there is a neglection of the temporal aspect during data splitting, such that there can be partitioning of data in a way whereby future data could be accessed by the algorithm, which will not be possible in an online setting or in a realistic setting. And in this example here of a random split, we can see that the RS is being trained on some data in T3 and T4, and yet it is being tested on a time step T2 here. So there is some excess of future data here causing the data leakage. And based on our definition of data leakage, we found that of the 12 toolkits that have been studied, listed earlier, none of the toolkits follow these global sliding windows that adheres to or conform to the data leakage defined in Prof. Soon's paper. Next, for the ambiguous metrics being defined, matrices currently that are defined without a temporal context and with ignorance to temporal ordering stemming from the first issue. And to expound a little further, Now, if a system evaluates a precision on interactions from its training data, and the precision obtained is high, we have to ask ourselves this question: is the precision high over all historical interactions, or is this just a current interaction, meaning a reflective one of the user's current interest? And this precision score can appear to be satisfactory, but fails to capture relevance over time, leading us to ask a question: this is precision at what time step? And finally, in the online simulation, the inadequacy in the online simulation, currently how the online platforms function is that when a customer visits the platform, like say online shopper in this case, will request for a recommendation, which the recommender system will return to the customer. A ground truth will then be obtained when the customer actually interacts with the platform, and this ground truth is returned to the recommender system for further training to update its belief, overall forming a feedback loop. And this is something that toolkits have yet to adequately capture, forming the three gaps. And with these three gaps identified, we aim to fill these gaps with Streamsight, where Streamsight has three overarching objectives. The first, a framework to account for the temporal context when building toolkits. Second, a simulation of an online setting in a more realistic one. Third, a push for an adoption of standardization of temporal handling. And with that, we would like to touch on the design on how Streamsight achieves these three objectives. And how I would be discussing the design would be a solution for a gap that is identified. And in the first gap on a data leakage, we propose the global sliding window that has been defined in Prof. Soon's paper. And how it will work is that the recommender system will always be trained on release data and evaluated on unreleased data at some time step ahead. To do this, we first sort the data set in temporal order, define a window size of 1 month in this case, and we can then perform the data split. So the background data would be the release data, the unlabeled data set would be unreleased data ahead of the timeline that the algorithm is in. And to evaluate based on the ground truth, we can derive the labeled data set from the incremental data set. And we can iteratively run through this loop across the data set and by citing the timeline forward. With n iterations, we can obtain several splits, which we can then group into these four overarching data sets. The first, the background data for initial training, the unlabeled data set, the unreleased data for prediction to be made on, the labeled data set for evaluation purposes that provides the ground truth, and third, or the last, the incremental data released post-evaluation for incremental training and update of its beliefs. Now, in the second gap, we propose that we will first respect the temporal ordering during evaluation and to have metrics with temporal tagging. And how this can be achieved would be first, we will list our ideal evaluation scheme, the ideal form, and what we have implemented based on the computation limits that we have seen and faced throughout this development. And in the ideal evaluation, we have the ground truth for a given user, and an algorithm, in this case, a prediction for a top 3 prediction for every test instance that we are getting the algorithm to predict on. So we assume the algorithm is trained, and the algorithm will now have to perform a prediction or 3 predictions for every test instance that we supply to the algorithm. And we can then generalize this problem as a prediction of across n users in a given window, where the prediction is done while respecting the temporal order in which the test instance occurs. So in this case, the misalignment of the test instance is intended because we want to bring across the notion that the prediction and evaluation should be done based on the occurrence of the test instance. And we can quickly see that there is a limitation in the compute power needed. So the total number of predictions can be formulated as the total test instance multiplied by the total number of users, both of which scale on window size and the data set. So by increasing either, we may see that this may not be a scalable solution. So instead, what we can do is, or in our implementation, we relax the assumption of needing to predict for every test instance, but rather we can group the test instance in a given window such that only a single prediction needs to be done for that window. And we can now generalize this problem to be a single prediction for every user in the given window, where the temporal ordering of the test instance in a given user is ignored. We can now simplify the formulation to be as such. It's a linear scale with the total number of user. And the performance gain can be seen when we assume the total number of test instances to be 10. Then in this case, it's a 10 times reduction in computation. Now, in the last gap that we have identified, an inadequacy in the online simulation, what we propose is to really mimic that online data communication through streaming and decoupling of the recommender system algorithm. And in fact, in our project, we developed two approaches. The first, the pipeline approach, which is what we see in current toolkits today, but with the added element of the temporal context. The second, a streaming of the data set through API calls where the recommender system is decoupled from the evaluation platform Streamsight. Now, I will first touch on the pipeline structure followed by the API structure. And in the pipeline structure, what we would first do is to perform the data split with the global timeline as discussed earlier. Now, in the pipeline phase, we will have different phases, the pre-phase, evaluation phase, and data release phase, all of which follows a looping feedback loop, which we talked about in the online setting. So in the pre-phase, the algorithm will be first trained. And what will happen is after training, we will now have to evaluate the algorithm. The algorithm will be made to predict on a data set in a forward time step and evaluate, and it will be evaluated based on the labeled data set derived from the incremental data by Streamsight. And once that is done, we can then slide the global timeline forward, and we will then release the incremental data set to the algorithm to update its belief. And we can follow this looping cycle like what we have defined in an online system, such that the global timeline is always slide forward, such that we slide the global timeline forward to respect and to prevent the data leakage. Now, this is the pipeline flow. In the streaming through APIs, what is the key difference would be now the RecSys and Streamsight are decoupled as separate entities. So they can be instantiated separately, where Streamsight now acts like a black box service to evaluate the recommender system. And how this can be done, which I will briefly walk through, would be we first register the RecSys with Streamsight to make its existence known. And subsequent phases will be similar to the pipeline, where the difference is now that Streamsight becomes a platform to evaluate the recommender system, where the RecSys that communicates directly with Streamsight as a platform. And like in the online setting, the API calls are made by the RecSys and Streamsights, and Streamsight only provides a response when the model makes a correct API call. And we can show an example where in an expected scenario where the RecSys has to make a submit prediction call, but instead makes a wrong call, what Streamsight will do is Streamsight will then raise a warning message to the RecSys. So now functioning as if both are separate entities that have independent choices. And this really is to bring back this diagram that we discussed earlier on the data communication and the creation of the feedback loop. And with that, now we want to talk about the results that we have obtained through the implementation of this design in Streamsight. And what we see now is Streamsight is an open source project available on GitHub. And we provide user documentation online as well, hosted on GitHub pages through Sphinx. So developer and user documentation can be easily obtained for references to develop or even use the toolkit. We also have a poster infographic that provides a quick overview of the project. As for the use case of the library, the Streamsight is designed to be easily installed with the Python default package manager or any other package manager like Poetry should the user want to use a separate library handler. Type hinting is provided in our library where in supported IDEs such as VS Code or PyCharm, where the user is able to get type hints from the different parameters quickly. Docstring support as well if the user does not want to open a web page beside his coding development platform. In overall, we have developed 9 modules and we have over 3,599 lines of code to support the robust library that Streamsight works on. Various debugging methods are also available depending on the choice of the objective of the developer, where the developer can choose whichever mode and suppression of warning if he needs to. And finally, we want to talk about the interface that we have designed. And the interface is one that is similar to that of scikit-learn, of interface that is very familiar to a lot of developers who are working in the machine learning environment. So this is an example of the load and split phase, which can be done through definition of the various parameters easily in code. And in the pipeline that we have talked about earlier, addition of new algorithms and matrices can also be done in a few lines of code. And in the streaming of the APIs, these are some of the simple APIs that can be made, designed to be intuitive to the user to quickly use the library. As for evaluation purposes, we provide 4 different levels of evaluation with different varying granularity of information required by the user for evaluation purposes. And over here, we want to provide a quick comparison of Streamsight to other toolkits that are still being used in 2024. And what we see here is that Streamsight currently is the only library that has been developed in 2024, which adheres to that global timeline definition which Prof. Soon has defined in his paper. And although Streamsight conforms to setting 1 and 2, which is one with the global timeline, it does not necessarily provide support for other settings as we see in other libraries. So where setting 3 to 5 are partial to no observance of the temporal element. Now, with the results defined, we would like to talk about some future works that can be considered for Streamsight for further development. And in the first future work that could be considered is the supporting attribute in the data set, which can be then brought over for a better contextualization when building the rexes. So right now, only the item user interaction along with the temporal context is considered. But in fact, other data points can be considered, say, for example, location data or any other kind of metadata, which can be injected into the data set to overcome the issue of data sparsity and to also provide a more rich context to the recommender system algorithm to formulate a prediction. In the second future work, which would be to bring Streamsight as an online evaluator. Streamsight currently runs locally on the developer's computer, not as an online service. And what we can do is to bring Streamsight online such that a central platform can be provided for evaluation purposes that conforms to this framework, thereby hitting the third objective of Streamsight as a toolkit to provide that standardization of handling of the temporal element, something that the person who will be taking over my FYP from would be working on right now. Now, to provide some concluding remarks, for this presentation, we first discussed and expounded on the gaps from the various toolkits that we have identified, and we also talked briefly on its impacts in the learning setting of the Rexes. We then highlighted how Streamsight implements solution to counter some of these gaps that we have identified. And in her design, we talked about the results that has been achieved and the type of interfaces that the developer can seek to use. And before I conclude this entire presentation, what I want to do is to reiterate the goal of Streamsight. And that is Streamsight is meant to bring forth another perspective of user decision modeling, to bring offline evaluation to that of a closer one, which we see in online settings. And this ties in closely with the provision of a standardization of a global timeline scheme to push the community forward into considering something of one that is a truly complex dynamic nature in a user decision modeling model. And we hope that Streamsight would now be a push and call to the community for an advancement towards this direction that is envisioned by Prof. Soon and what he has highlighted in his paper. Thank you very much. Yeah.